All right, today's lesson is on conditional probability. The probability that one event happens, given that another event is already known to have happened, is called a conditional probability. Suppose we know A has happened, then the probability that event B happens, given that event A has already happened, is denoted by B, and then that straight up and down line right there we're going to be given. So the probability of B given A. If the order does matter in most of these problems, A given B, the top of the fraction is the intersection of the two events. The bottom of the fraction is dividing by whatever the second thing is. The probability of B given A, top of the fraction is still the intersection, and we're dividing by the second thing here, which is the A. Okay, revisiting a type of problem we've seen before, but now we're going to address it with the new formula. What is the relationship between educational achievement and home ownership? A random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. The two-way table displays the data. Okay. Question A. If we know that a person owns a home, what is the probability that the person is a high school graduate? Now, we've answered that question before by kind of using somewhat common sense two-way table approach, but now we're going to do it as a formula-driven approach. So, translating, if we know the person owns a home, what is the probability the person is a high school graduate? So it's a probability that they're a high school graduate given that they own a home. Okay, if we know they own a home, that's the given. So the formula is probability of A given B. So A is high school graduate, B is own a home. The top of the fraction is going to be the intersection of those two things. The bottom of the fraction is going to be that second thing, the B, where you own a home. So the AND is going to be the 221 out of 500. That represents the group of people that are both high school graduates and homeowners. So 221 out of 500. And then the probability of B is the probability that you own a home. The probability that you own a home is 340 out of 500, and that gets you the 0.65. Okay, to illustrate that the order typically does matter, if we know the person is a high school graduate, what is the probability the person owns a home? So it flips the order in terms of which is the probability that you're finding, and then which is going to be the given. Well, the top of the fraction is still the same. For intersections where there's A intersects B or B intersects A, that doesn't change. What changes is the bottom of the fraction. It's the second thing, are you a high school graduate? That's the bottom of the fraction. So the high school graduate is the 310 out of 500, so it changes the probability from 0.65 to about 0.713. When you're working with two-way tables, sometimes you work off of actual counts, like we did here. Sometimes you work off of percents or proportions, like is being asked here. The following table classifies U.S. households according to the types of phone they use. So, do you have a landline or not? Do you have a cell phone or not? Problem. What is the probability that a randomly selected household with a landline also has a cell phone? So, what's the probability of a randomly selected household with a landline? That's the given. So, it's known that they have a landline. Okay, they also use a cell phone. So translating that into the way it needs to appear to use this formula, it's the probability you have a cell phone given they have a landline. So using the formula, the top of the fraction is the intersection of these two guys. That's the cell phone and the landline. That's 0.51. Divided by the second thing, which is landline, the probability of a landline is 0.6. So there's about a 0.85 probability that a landline user also has a cell phone. Now, these are pretty clean compared to what we're going to be doing in the big picture of things in this class. Rather simple probability problems. We don't necessarily have to be using this formula. Both of those questions could be answered using other strategies we've done in the class, but we are going to have to use those formulas for more advanced problems, so we need to build up to being comfortable reading those formulas, knowing what to plug in for the easier ones if we're going to understand the harder ones at a later time. Right, the probability that events A and B both occur can be found by using the general multiplication rule. The probability of A and B is the probability that they both occur. Those two things mean the same thing. And that, using the new formula, is the probability of A times the probability of B given that A has already occurred. Where probability of B given A is the conditional probability that event B occurs given an event A has already occurred. In the special case of independent events, the multiplication rule becomes, so if they're independent events, meaning the first thing has no impact on the second thing, you're simply multiplying the two things together. If the first thing has an impact on the second thing, they're not independent, then you have to take into account that conditional probability that the first thing already occurred. All right, starting off with some basic ones that don't necessarily require this rule. We've seen these before, but just identifying, well, when does the first event affect the second event? Okay, so for the following problems, use this information. We have 3 different jars with a number of marbles of different colors in each. So for this first one, 2 marbles are randomly drawn one at a time with replacement. If you are choosing things with replacement, that's an indicator that we have independent events here. If it's with replacement, that means that after we choose the first one, it goes back in. So that first choice doesn't affect the outcome of the second choice, which means we're using this version of the formula right here, where we're simply multiplying the two probabilities together. So we're in jar 1, the probability of choosing a blue, then a white. That would be 4 out of 10 times 2 out of 10 with replacement is simply multiplying those two probabilities together. Okay, question number 2. 2 marbles are randomly drawn one at a time from jar 1 without replacement. What's the probability of blue and white? So it's the same basic question with the with replacement, without replacement changing. Well, whether or not the first one gets put back has no impact on the first pick. The probability of the first one being blue is just 4 out of 10. But if that blue one doesn't go back in before we pick the next one, then that outcome affects this outcome. It changes the probability of the second choice. So we have to adjust the fact that this isn't 2 out of 10 because only 9 marbles in there. That first blue one didn't go back. Of the 9, both of them are white. We get a similar probability, but a little bit different. Now, for the choosing marbles, using this formula really doesn't apply. The goal here is more identifying when do we have independent, when don't we have independent, when do we have to adjust that second fraction. And when we get into more higher end problems, we'll be adjusting the second fraction using the formula from the first page. Okay, a couple more examples. 2 marbles are randomly drawn one at a time from jar 2 with replacement, probability of black, black. So 4 out of 8 chance of picking a black. If it's with replacement, it's the same exactly 4 out of 8 chance for the second pick. Okay, 4 marries up or pairs up with 3. We're in jar 2. We're still interested in the black-black combination, but now it's without replacement. The first choice doesn't matter whether it's with or without replacement. The second choice, we need to know, did the first one go back or not? If the first black didn't go back, there's 1 less marble, and there's 1 less black one in there. Okay, this idea here is not limited to just choosing 2 things. It could be choosing 3, 4, 5, an unlimited number of things. I'm not going to go through in detail question number 5 in the interest of time here, but that's just an example of multiplying 3 fractions instead of 2 fractions. All right, another common scenario with introductory probability problems deals with decks of cards. Okay, 2 cards are randomly chosen one at a time from a standard deck of 52 cards. The first card is not replaced before the second one is chosen. Find each of the following probabilities. So if we are choosing 2 cards without replacement, not replaced, right here, we know the bottom of the fraction is going to be 52, 51 for each one of these guys. It means we have a conditional probability. It means what happens on the first pick affects the second pick, because there's a different sample that we're choosing from when we make the second pick. Okay, both cards are face cards. There are 12 face cards in the deck. So 12 to choose from for the first one, and then there's one less for the second pick. The first card is an ace, the second card is not an ace. Well, there are 4 aces in the deck. If the first one we chose was an ace, all the not aces are there for the second pick. There are 48 cards that are not aces. Both cards are diamonds, 13 diamonds in the deck. So if the first diamond doesn't go back, there are 12 left to possibly pick for the second one. The first card is black, the second card is red. Well, half the deck, or 26 out of 52, are black. If the first one we chose is black, all 26 of the 51 remaining cards are there to choose from for the second pick. The first card is a club, 13 out of 52. There are 13 of every suit. And the second card is black. Well, the club is a black card. So the original 26 black cards in the deck, there is only 25 remaining for the second pick, because that first one we chose was a club, which is black. All right, next scenario. Suppose you are taking a 10-question multiple choice quiz. Each question has 4 options. If you randomly guess for each question, what is the probability that? Or if you're taking a 10-question quiz, it means you're making 10 choices. If you are randomly guessing, that means what you guess on one question has no impact on how you guess on the second question. So if there are 4 options, you have a 1 out of 4 chance of getting the first one right. Randomly guess on the second one, you have a 1 out of 4 chance of getting the second one right, etc., etc., etc. So it's 1 out of 4 times 1 out of 4 times 1 out of 4, or grand total of 1 out of 4 to the 10th power. So your chances of getting all 10 questions correct are not looking so good. What's the probability that you get all 10 questions incorrect? Well, if there are 4 choices, 1 of them is correct, 3 of them are not. So you have a 3 out of 4 chance of getting a question wrong. So 3 out of 4 in the first one, 3 out of 4 in the second one, 3 out of 4 in the third one, etc., or 3 out of 4 to the 10th power, a 5.5% chance that you get all of them incorrect. Okay, the first question you get correct is on your 4th guess. So that means the first guess is wrong, the second guess is wrong, third guess is wrong, 4th guess is correct. So you have 3 incorrect, and then the 1 correct at the end. And as long as they're saying randomly guessing implies what you guessed on the first question has no impact on what you guessed on the second question, etc. Okay, you get all of the even numbers correct and all of the odd numbers incorrect. So the first one's an odd number, that's incorrect. 3 out of 4 chance of that happening. Second one's an even number, you get that correct. 1 out of 4. And 3 out of 4, 1 out of 4, etc., etc., etc. And you get about a 2.3 times 10 to the negative 4th chance of that occurring. All right. Now, the common theme for 1, 2, 3, 4 in this section is we know specifically on each guess whether we're interested in the guess being correct or incorrect. Now, in contrast, number 5. 5 of the 10 are correct and 5 of the 10 are incorrect. Okay, we don't know which ones are the correct, which ones are the incorrect. Maybe it's this. Maybe it's 5 in a row correct, 5 in a row wrong. Maybe it's right, wrong, wrong, right, wrong, wrong, right, etc. There's lots of different combinations of ways to guess that will produce 5 correct, 5 incorrect. So that adds a layer of complexity that we don't know just yet. This question is a more complex scenario that we cannot reasonably solve with the general multiplication rule. We'll revisit this at a later time. It turns out this isn't a very difficult question. We're going to learn how to do this next chapter, just based on the probability we know right here, right now. This basic multiplication rule we've been using isn't going to work. All right, let's look at this same idea now in the context of rolling dice. Consider rolling a standard fair 6-sided die 5 times. What is the probability that? Okay, if you're rolling a dice or a die what you get on the first roll does not impact the second roll, which does not impact the third roll. They're independent events. This is basic, simple multiplication rule. So rolling a 6, you have a 1 out of 6 chance of rolling a 6. You have a 1 out of 6 chance of rolling a 6 the second time. 1 out of 6 chance of rolling a 6 the third time, etc., or 1 out of 6 to the 5th power. Okay, what's the probability that none of the rolls are a 6? Well, there's a 1 out of 6 chance of getting a 6. There's a 5 out of 6 chance of not getting a 6. So 5 out of 6 times 5 out of 6, etc., 5 out of 6 to the 5th power. The first 6 you roll occurs on the third roll. So not a 6, not a 6, 6. The outcome of the 5 rolls is as follows. Even number, odd number, prime number, multiple of 3, factor of 12. The connecting feature of all 4 of these is the same connecting feature as the first 4 of these. We know exactly what we're interested in on each individual specific roll. If we know what we're interested in on each individual specific roll or each individual specific guess of a question, then we can use basic fundamental counting principle rule here, or general multiplication rule. Sorry, quoted from a different book. All right, now in contrast, number 5, exactly 2 of the 5 rolls are a 6. Well, we don't know which of the 2 rolls are going to be a 6. Is it the first and second? Is it the first and the third? Is it the second and the fourth? So this falls into the same category as number 5 did up top. This question is a more complex scenario that we can reasonably solve with the general multiplication rule. Again, this is not a difficult question. It's just we don't know the math yet. That's going to be something else we revisit in Chapter 6. Okay, back to cards. Consider choosing cards randomly one at a time with replacement from a standard deck. What is the probability that the first club chosen is on the third attempt? So, not a club, not a club, club. It's with replacement, so that means these events are independent. The bottom of the fraction stays 52. We're choosing from the exact same set of 52 cards for each pick. 39 non-clubs, 39 non-clubs, 13 club. All right, similar scenario, except now it's without replacement, rather. Consider choosing cards randomly, one at a time, without replacement from a standard deck. What is the probability the first red card is chosen on the fourth attempt? So if we're choosing without replacement, these are dependent events. That means what happens in the first pick affects the second one, which affects the third, which affects the fourth, etc. So now the bottoms of the fractions are going to be 52, 51, 50, 49, because the cards aren't going back after we pick them. So not a red card, not a red card, not a red card, red card. So all 26 non-reds are there for the first pick. That doesn't go back. So of the 51 cards that remain, 25 of them are non-red. Same story here. When we make that last pick, there are 49 cards to choose from. We're getting a red here. This is the first time we take one. All 26 reds are in the deck. So a little bit better than a 6% chance of that occurring. That covers what we need to know for today's lesson.